Welcome back to the second video for TEC 293 on Thursday, March 4th. The purpose of this video is to discuss non-ferrous metals. Now you might remember that the definition of ferrous metals is that they contain iron, and so the definition of non-ferrous metals is that they don't contain iron. If you look at the periodic table, however, there's a lot of metals that don't contain iron in them. Remember the periodic table, like the leftmost 2/3 of the periodic table, those are metals. So instead of talking through all 70 or 80 or 90, or I don't know how many, there's a lot of non-ferrous metals. What I'm going to do is pick half a dozen of what I would say are the most important non-ferrous metals. And we'll talk a little bit more about each of those half dozen non-ferrous metals that I would say are really important to our society and our way of life. So let's go ahead and switch over to the slides and we'll start talking through non-ferrous metals. Okay, non-ferrous metals, let's get started. So we're going to talk about half a dozen different non-ferrous metals. The most important one probably is aluminum. It's very widespread, used for lots of different applications. Oftentimes, it can substitute for steel in certain applications. Aluminum is not as strong as steel, but it's also less dense than steel. So there are certain applications when maybe you don't need that strength of steel and you'd like to save some weight, and so aluminum is a good alternative. You might remember a couple of years ago there was a kind of a flap when Ford started using aluminum for the bodies of the beds of their pickup trucks. And of course, Ford says that it's perfectly adequate and it saves a lot of weight, which increases the towing capacity, and was touting the benefits. And of course, Chevy said that it's not as strong. And so they did some demonstrations where it's possible to puncture the bed of the pickup truck. So, there's some debate there. But the point is that there certainly are some applications where aluminum is a good choice because it's a lot less dense than steel. And if you don't need the strength of steel, then you can often get by with aluminum. Aluminum is oftentimes easier to work with and lighter. Copper, we'll talk about copper in not quite as much detail as aluminum. Copper tends to have a very good conductivity, so it's good to make things like wires out of. It's also very ductile, so it's easy to make wires and different shapes of materials. Brass is the next thing that we'll talk about. It's pretty easy to make things out of. It's pretty ductile, depending on the amount of zinc. The amount of zinc in the brass determines how hard it is. And the more zinc it has, the harder and the stronger it is. The less zinc it has, the more ductile it is and easier to work with. The fourth one we'll talk about today is lead. The big thing about lead, it is very dense. And so for applications where you want a really massive part, then you might want to make it out of lead. Magnesium. Magnesium kind of is to aluminum what aluminum is to steel, in the sense that if you've got a part that doesn't quite need the strength of aluminum, but you want it to be very lightweight, if lightweight is really important, then magnesium might be a good application. It's not as strong as aluminum, but it is less dense than aluminum. And its strength to weight ratio is very good. The last one we'll talk about today is zinc. Zinc is often used as an alloying element to make things stronger and harder, and it also has very good corrosion resistance, so that property is useful as well. All right, we're going to talk more about aluminum than any of the others because aluminum is the most commonly used of these non-ferrous metals, and it's arguably the most important of these non-ferrous metals. Interestingly, aluminum is really common. Aluminum is actually the most abundant metal in Earth's crust. All right, so you can't just say in all of Earth because we know that Earth has an iron core. So if you include all of Earth, then okay, iron is the most common metal. But if you include just the crust of Earth, it's actually aluminum. Aluminum is the most abundant metal in Earth's crust. It's also the third most abundant element overall behind oxygen and silicon. Oxygen is obviously found in the gaseous form in the air that we breathe, but a lot of oxygen is actually formed by reacting with solid materials. So things like iron oxide, we'll talk about this, aluminum oxide is mainly how you find aluminum in the crust of Earth. So you don't generally find pure aluminum, you find it bonded with oxygen in the form of aluminum oxide. Anyway, oxygen is the most common element. Silicon, which normally takes the form of sand, is the second most abundant element in Earth's crust, followed by aluminum. Like I just said, normally you find aluminum as aluminum oxide rocks. They're rocks that contain aluminum oxide. That's the way you find it in nature. And another word for aluminum oxide containing rocks is bauxite. Bauxite is a type of rock that has a lot of aluminum oxide in it. So we can use that and react it with a bunch of other chemical elements, kind of like we did in the steel production process, but the aluminum production process is a little bit different than the steel production process. But basically we're going to take the bauxite rock, or the crushed alumina, and we're going to crush it first, and then we're going to react it, and we're going to produce our pure aluminum. The method that we use to create or produce this pure aluminum is called the Hall method. It's named after a guy named Charles Hall, who lived and worked outside of Cleveland, Ohio. And it's kind of interesting. There's a direct lineage between Charles Hall and what he did a century and a half ago to the modern aluminum company called Alcoa. And you may have heard of that. Alcoa is a big aluminum company. It's ALCOA, stands for Aluminum Company of America. And they have a whole bunch of production facilities, including, if I recall, they have one aluminum production facility near the Quad Cities on the Mississippi River of Illinois. Anyway, so the Hall method is the most important production method for aluminum, and it's kind of similar to the electric arc furnace for steel production. So here's what that looks like. Once again, like the steel production, I don't need you to know the chemical symbol or formula down here, but it's helpful to look at. Basically what we're doing is we're combining aluminum oxide, aka alumina, and we're combining that with carbon in the presence of a lot of heat and some reacting agents that we'll talk about in a minute. And that gets reacted and you form aluminum, pure aluminum, which is what we want right there, and a lot of carbon dioxide, which is kind of unavoidable. So you produce a lot of carbon dioxide in this process as well, and use a lot of energy as well. So this is our vessel for aluminum production, and you can kind of see some similarities between this and the electric arc furnace for steel production. These are our electrodes right here, and they are conducting electricity through all of this material to the cathode. So you've got electricity flowing from here and here and here through this material. There's electric current going through this material, heating it up, and the current is going to the cathode and out to ground out there. So the inputs that you put into this material, it requires alumina, which is aluminum oxide powder that comes from those bauxite rocks. You also need this reacting agent called cryolite. It has sodium and aluminum and fluorine in it. And that fluorine, well, it helps the chemical reaction proceed at a lower temperature, but it's kind of nasty stuff, and it results in some kind of nasty outputs from this process that we'll talk about in just a moment. And the other thing you need is a lot of electric current. There's a lot of heat that is required, and so it takes a lot of current and thus a lot of electrical energy. What you get out of this process, you get your molten aluminum, which is right here. That's really the desirable output. You also get a bunch of waste gases, carbon dioxide, and some fluorocarbons, which are even less desirable than carbon dioxide, but it's a byproduct. This last one is actually the most problematic, though. There's something called spent pot lining. So this is the liner of the pot that you're doing this reaction in. And because of this cryolite, specifically because of the fluorine, you get some pretty nasty stuff that is contained in this spent pot lining. Things like fluoride and cyanide are some pretty hazardous and pretty nasty materials that are results of this process. And so they have to be basically sealed up and disposed of as hazardous material. You can't just dump them in a landfill. It has to be carefully and properly disposed of, and it takes up space somewhere. All right, and then another output is something called red mud. This is basically what's left over from all that rock, aside from the good stuff, which was the aluminum oxide. All right, so whatever was left in that rock is not useful to this process, and so it's just left over. We call it red mud, and the red color comes from the fact that these rocks also contain typically some iron, and so that's not very useful. Normally that stuff is just dried into a solid and then just stored, basically. It's not very useful for anything. All right, anodizing is a really important process for aluminum, and we've talked about this a little bit when we talked about stainless steel. It's a very similar process. So what anodizing does is that it actually oxidizes part of the material, the outer layer of the material. And the important part about oxidizing aluminum, and this is also true of other materials like stainless steel and magnesium as well, to name a few others, titanium also. The important part is that when it oxidizes, it doesn't flake away or disintegrate. It remains part of the lattice structure of the material. And that's the big difference between aluminum oxide, titanium oxide, magnesium oxide, chromium oxide for the case of stainless steel. The difference between those and iron, because when iron oxidizes, it forms iron oxide, and that does not remain part of the lattice structure. It flakes away, it falls apart. So anodizing or oxidizing these other materials like aluminum and titanium and stainless steel and magnesium, that actually prevents oxidation from happening inside the material. It's only in the outer layer that gets oxidized. Because, and you say, why is that important? Well, when you oxidize a material, it does change the material properties. So if you had a whole material that was aluminum oxide, if the whole thing was aluminum oxide, that would not be very useful for us. It wouldn't have the desirable mechanical properties that aluminum does. So it's good that only the outer layer of the part gets oxidized and forms aluminum oxide. The rest of it stays whatever the base material is, mostly aluminum with some alloying elements added in as well. All right, anodizing is a process where you put the aluminum part in an acid bath, and then you run electric current through that acid bath. And what that does is it speeds up the oxidation process for the aluminum. So when you anodize a part, you build up an oxide layer around the outside of that part, and that actually protects the inner parts of that specimen from getting oxidized themselves. One kind of cool thing about anodizing is that you can add dye or pigment to that acid bath that you're putting the material into, and that is actually going to color the material. So this pigment right here is actually reacted into the material, so it's not going to easily wear off like paint would. This is a much more durable pigment than paint would be, but it is notable that it's only on the outside layer of this part. So if you were to cut through this specimen right here, it would not be blue all the way through. It would be the normal kind of gray aluminum color in the middle. It's only blue due to the anodizing or oxidizing that happens on the outer layer of the part. All right, some important mechanical properties about aluminum is that it's about 1/3 the Young's modulus. It's also about 1/3 the strength of steel, and it's also about 1/3 as dense. So it's a trade-off, and lots of times that is a good trade-off to make. Lots of times you don't need the full strength of a steel part, and an aluminum part will suffice, reasonably well. And the benefit is that it's only 1/3 as dense. So for a given dimension, it's only going to weigh 1/3 as much. Aluminum is also kind of nice to work with. It's relatively soft and ductile compared to steel. And so that makes it pretty easy to extrude. What extrusion is, you may have talked about it in a previous class, a manufacturing class, but basically extrusion is pushing the material through a die or a form. So you have this hunk of aluminum, you push it through a die, and out the other side you have a material in the shape you want. So all of these materials, these specimens right here, all of these were extruded. They were pushed through a die that had these funky shapes, and what you get out the outside is a specimen that has these desirable shapes. So lots of good structural applications for these types of extrusions. All right, how do we name aluminum? Remember, we talked about naming steel. Remember, we talked about 1018 steel. What does the 1 and the 0 and the 18 mean? What does that all mean? Now we're going to talk about the same thing with aluminum, because we've dealt already in this class with 6061 aluminum and 7075 aluminum, and there are hundreds, if not thousands, of different types of aluminum. If you go on a metals distributor website, you can specify what kind of aluminum you want, and so you have to know something about, well, what are the different properties that the different types of aluminum are going to give me. So the nomenclature that you will see with aluminum, it's usually 4 numbers, and then sometimes those 4 numbers are followed by a letter. So you see 4 numbers dash a letter. Sometimes. You don't always see a letter right here. The first number in that 4-digit sequence refers to the primary alloying elements. So that's what else did you add into the aluminum so that it's not pure aluminum. The ones I want you to know here, the ones I would want you to memorize because they're the most useful, are the 1 series, which is really just pure aluminum. Doesn't really have any alloying elements, and the 6 series and the 7 series. The 6 and 7 series are the most common types of aluminum that you will see. The second digit in the 4-digit number is basically a quality control modification. Sometimes it's a 0, like in the case of 6061 or 7075. So if that second digit is 0, then it doesn't change anything about the allowable percentage of the alloying elements here. But if it is, there is such thing as 7175 and 6161, then it changes something. You have to actually look it up exactly what is changed, but it does change the amount of allowable alloying element in the specimen. The 3rd and 4th digits are this is a little bit weird. It's different than steel. Remember, steel, actually, the last 2 digits stood for how much carbon was in the steel, but the last 2 digits of the aluminum numbering system actually refer to a chronological sequence of when it was developed. So the 6001 came first, and then 6002, and then 6003, and then you know, approximately 60 iterations later, they got to 6061. So 6061, if we take that as an example, because it's a really common aluminum, 6061, it contains magnesium and silicon as alloying elements. The second digit, 0, tells us that there's no quality control modifications. It's just this. It's just aluminum, magnesium, and silicon. And the last 61 tells us that it was the 61st such aluminum alloy developed based out of magnesium and silicon. The fifth letter, that is this one right here, that's the only letter, that designates the heat treatment if it's applied. And the most common ones are O and H. O indicates that the material has been annealed, which we'll talk about in a few weeks. But annealing, what it does is increase the ductility of the material. And it could also be an H. The letter could be an H. If it's an H, that means it's been hardened. So that has increased the hardness of the material, and likely also the strength at the same time. All right, so a couple of examples. We just talked about this. 6061-O means it contains magnesium and silicon. That's what this 6 means. 0 here means it doesn't have any quality control modifications. It's just the naturally occurring levels of impurities. And the 61 means it was the 61st such alloy developed. And the O means it has been annealed to increase the ductility of the part. 6161-H basically just means it's a slight modification of 6061. It changes the allowable percentage of alloying elements or changes the allowable amounts of impurities in the part. And the H means that it has been hardened, work hardened, to improve the strength and the hardness. All right, the exception to all of this is the 1 series, which is one of the ones that I want you to know about. The 1 series is pure aluminum, so it doesn't contain any alloying elements, but it can contain some impurities. And the last 2 digits in the 1 series tell you how pure is the aluminum. And those last 2 digits are to the 100th place of a percent between 99 and 100%. All right, so if it's 1030 aluminum, then it contains 99.3% aluminum. If it's 1060 aluminum, then it contains 99.6% pure aluminum. And once again, the O means it's been annealed. Okay, so we're not going to talk about the rest of the materials as in the same level of detail that we talked about the aluminum. Mostly just one slide for the rest of these. Copper tends to be fairly expensive and tends to be a soft and very ductile material. But probably the most important thing to know about copper is that it has really good conductivity, both electric conductivity and also thermal conductivity. It can conduct heat and electrons very effectively, very well. And so it tends to be used most commonly for electric wires, like the wires in your house. The other option for electric wires is aluminum. And actually for large transmission lines, you know, the kind that go from city to city, those are actually aluminum. But aluminum has a higher resistance, and it's a little bit harder to work with. They did used to make homes with wires made of aluminum, but what they found is over time, it was more difficult to make those connections inside the home, and so they had a bunch of house fires. And so copper is a preferable material to work with, particularly for wiring inside a home, but it's more expensive than aluminum, and so that's why transmission lines are still mostly made out of aluminum. It's also really ductile, it's easy to work with. So the other really common thing to make out of copper, besides wires, is pipes. A lot of homes use copper piping for their water. Brass is the next one that we'll talk about. Brass is an alloy of copper and zinc, and you can change the relative amounts of copper and zinc. Generally, the more zinc you add, the harder and stronger it's going to be, and the less zinc you add, the softer and more ductile it's going to be. Brass is going to be stronger and denser than aluminum, but it's not going to be quite as strong or as dense as steel. One of the good things about brass is that it has low friction. So a lot of times it's useful in applications where you're going to be twisting something or sliding something or rolling something, like gears or valves, you know, all these places where you're going to be twisting or sliding or rolling something against each other. Brass works really well for that because of its low friction properties. So it's good to use in plumbing fittings. It's also common in musical instruments and gears because it has low friction. Again, rifle cartridges. Actually, rifle cartridges, one of the good reasons to use it for that is because it doesn't spark. Of course, if you fill it with gunpowder, the gunpowder will spark, but the brass itself will not spark. If you use brass with a lower zinc content, then it's easy to form and it's ductile. If you use a higher zinc content, then it's not so ductile, not easy to form, but it's good to cast with, and you can machine it fairly easily also. Lead is the next one. The most important thing about lead is that it's very dense. And so useful applications for a really dense metal are ship keels. You know, if you want to have a lot of weight on the bottom of the keel, fishing sinkers, you can use it to give weight and drop the bait down in the water. And it's also useful to protect against radioactivity. Because it's so dense, the radiation, depending on what type of radiation, has a hard time getting through the lead. One kind of interesting side note here, when I was in the Navy, I worked on the nuclear reactors in the aircraft carrier that I was on, and the shielding around the aircraft carrier consisted of two materials. First of all, it was quite a bit of water, because water is a fairly effective shielding material. It's not the best, but water is cheap. And the other shielding material that was used was lead. Lead is a lot heavier and it's more expensive than water. So we didn't use as much lead as we used water, but between those two things, water and lead, those were the shielding materials that we used to protect ourselves from the radiation in the reactor compartment. The next one is magnesium. Magnesium is a pretty exotic type of metal. I'd make the analogy that magnesium is to aluminum what aluminum is to steel. So magnesium is a very light metal. In fact, magnesium is normally regarded as the lightest or least dense structural metal. Magnesium is the least dense structural metal. So magnesium is lighter, less dense than aluminum, but it's also weaker than aluminum by a factor of about a half. So it's about a half the density, half the Young's modulus, and half the tensile strength of aluminum. And what you'll see it used for is some exotic applications where it's really important to save weight. So things like, really high-end bicycle components, the materials used for jet engines where they really want to save weight, especially the rotating components inside the jet engines. Magnesium is strong enough and it's heat resistant enough and it's very lightweight. So it's a good application for parts for jet engines. Notably, magnesium by itself, you may have seen videos of this. If you just take a chunk of pure magnesium and you throw it in water, you know what's going to happen? It's going to burn. It's going to catch on fire, and it's going to react strongly with water. So what we do is we don't use pure magnesium. We alloy it with other materials, and we also put surface coatings on it. So between the two of those things, between alloying it with other elements and putting a surface coating on it, that makes it so that it's not reactive with water. Zinc is the last one that we're going to talk about today. It's useful, but it's not very strong. It's pretty heavy. It's not very strong. But the useful part about it is, well, a couple of things. It is cheap, and it's also pretty resistant to corrosion. So you can use it for applications where you want to save cost, and you can also use it for applications where you want to prevent rust. It's not as corrosion resistant as, say, aluminum or stainless steel, but it's pretty good. You know, it's a lot better than plain old steel. So what's really common to do in things like fittings or screws or bolts is to take a layer of zinc and put it on the steel. So you have a zinc plating on top of the steel, and that increases its corrosion resistance. So that's a really common thing that you'll see in fittings and mechanical fasteners. It's also, it has a pretty low melting point, so it's pretty easy to cast, and it's not real strong, but it is cheap. And so you'll see it in kind of cheap applications like door hooks, where you want to make it really cheap, and can openers and handles and things like that. Doesn't have to be real strong, and the more important thing is that it's cheap. Also, it's an alloying element, so zinc can be added, especially to brass. And like I said before, if you add more zinc to the brass, then it tends to be harder and stronger. If you have less zinc in the brass, then it tends to be weaker and more ductile. All right, so that wraps up the discussion of the 6 non-ferrous metals. If I had to pick a 7th material to talk about, and I'm not, so this is not testable, but if I was, I'd probably pick titanium. Titanium you see in some high-end components like bicycles, some aerospace applications, places where you want to save weight. But titanium is a bit of a misnomer. A lot of people think that titanium is super lightweight and super strong, and that's actually not true. It is quite strong, and it has a very high strength to weight ratio. So for its weight, it's very strong, but it's actually more dense than aluminum is. So it kind of in terms of density, titanium falls in between aluminum and steel. In terms of density, it's probably closer to aluminum than it is steel. And in terms of its strength, it also falls between aluminum and steel, but it's probably a little closer to steel than it is to aluminum in terms of strength. So the best thing about titanium is it has a really high strength to weight ratio, stronger than, higher than aluminum or steel. So for some applications, that's really good, because if you want to make a component for a bicycle or something, you can make it relatively small, and because it has a high strength to weight ratio, it will serve the same purpose as a larger component that is made out of, say, aluminum or something like that. So titanium is not this like super lightweight, super strong material. It's a little more dense than aluminum, but it's considerably stronger than aluminum, not quite as strong as steel. So anyway, the material that is super lightweight and still fairly strong is magnesium. Magnesium is kind of the exotic material where you really care about lightweight, but it's also pretty expensive. All right, so that wraps up our discussion of non-ferrous metals. I will also say this is the last topic for exam 2. So you now have all the material for exam 2. So you can start organizing your notes and you can start preparing for exam 2. The rest of what we're going to do before exam 2 is we're going to do the lab 6, and then we're going to do a review So that's going to be it for now, and I'll see you in the lab.